So in this video we're going to look at partial fraction decomposition in the case where we have a repeated linear factor showing up in the denominator. So here's the integral that we are being asked to find. The degree of the numerator is less than the degree of the denominator, so partial fraction decomposition is something that we can try. We can look at factoring the denominator, which will be necessary if we're going to use partial fraction decomposition. So I'm going to rewrite the stuff inside the integral, the integrand, plus 1 over, and we have an x cubed minus 2x squared plus x. And if we're trying to factor the denominator, the first thing that we want to notice is that an x shows up as a factor in each of the three terms, so we can factor an x out of the denominator, which leaves behind an x squared minus 2x plus 1. And then we want to notice that this quadratic right here can be factored. So if I rewrite my numerator, I can factor this as x minus 1 times x minus 1. But x minus 1, which is a repeated linear factor, which is the case that we're looking at here, x minus 1 times x minus 1 can just be written as x minus 1 quantity squared. So if we're going to break this ratio into a sum of ratios, we're actually going to need to break it into three ratios. So the possibilities are something over x plus something over x plus 1 plus something over, not x plus 1, x minus 1 plus something over x minus 1 squared. And the idea is, if you've got a linear factor in here or a quadratic factor and it's being raised to a power, you need to have each possible power of that linear factor. So I need an x minus 1 to the first and an x minus 1 squared. If this were a fifth here, I would need plus something over x minus 1 to the fourth, or to the third, plus something over x minus 1 to the fourth, plus something over x minus 1 to the fifth. You would have to have all possible powers that could show up. And that's coming from, if you look back on the slide we had that summarized the different situations we can find ourselves in. If we factored ourselves into the form ax plus b to the m, then we're going to have ax plus b to the first, to the second, all the way through the mth power. So we'll have m, that will generate for us m distinct terms. So in this case, if this ratio can be broken into the sum of ratios, it may break into the sum of three ratios. And then we want to remember that the numerator always has to be the polynomial of degree 1 less than the denominator. So here x is a first degree polynomial, so we suppose that the numerator is an a. X minus 1 is still a first degree binomial being raised to a power, so we're just going to predict that we get a real number in our numerator. And this is being squared, but it is still a first degree binomial that's being squared. So it's a linear factor that's being squared. So we still wind up assuming that it's just a real number or a constant. In subsequent videos, we'll look at situations where we have to have something other than a constant in the numerator. So when you look at this, what you want to identify is the common denominator is actually going to be x times x minus 1 squared. So the first thing to do is look at that and say, what's my common denominator? Well, it's x times x minus 1 quantity squared. And then once you do that, you have to figure out what does each term need to be multiplied by to get the common denominator. And clearly the a over x that's sitting here, you would have to multiply it by an x minus 1 squared over an x minus 1 squared to get the common denominator. So my numerator is going to have an a times x minus 1 squared in it. The b is over an x minus 1, so we would need to multiply by x over x, and we would need to multiply by x minus 1 over x minus 1 to get x times x minus 1 squared. So plus b will be multiplied by x times x minus 1. And then c, to get the denominator of x times x minus 1 squared, we would just need to multiply by x over x. So this is going to be a plus a cx. And the idea is that the denominator is just the factored form of the original denominator. So the denominators already match. So to get the two ratios, this one here and this one here, to match, we need the numerators to match. So what we need is negative 2x squared plus 5x plus 1 to equal a times x minus 1 quantity squared plus bx times x minus 1 plus cx. We need the numerators to match. And again, this is a matter of going and picking out smart choices for x and plugging those values of our x in. So the first smart choice for x would be plugging in a 1, because if we plug a 1 into x minus 1, we get a 0. So choose x minus 1 as a choice. When we plug in 1 here and here, we're going to get negative 2 plus 5 plus 1. We're going to get a negative 2 plus 5 plus 1 equaling, we plug a 1 in here, we get 1 minus 1 is 0. 0 times a is 0. 1 minus 1 is 0. 0 times stuff is 0. We just get a c times 1, or c. And we get negative 2 plus 5 is 3 plus 1 is 4. We get 4 is equal to c. So there's our first value. And once I know what c is, I can actually go here and replace that c with a 4. The next good value to choose would be x equal to 0, because if we choose x equal to 0, we'll zero out each of these two terms. So good choice is x equal to 0. When we plug in x equal to 0, we get just a 1 on the left-hand side, because negative 2 times 0 squared plus 5 times 0 plus 1 is just 1 equals. When we plug in 0 on this side, both of these terms zero out because we get multiplication by 0. So we get a times 0 minus 1 is negative 1 squared. We just get a times negative 1 squared. So we find out that a is just equal to 1. So there's our value for a. And then when we look at it now, we see that there are no sneaky values to plug in for x anymore. So now you just pick something that will make small numbers. So negative 1 would be a good choice because it would be easy to work with over here. 2 would be a good choice because we get some 2 minus 1s gives us 1s, and 1s are easy to multiply by. There's more than one good choice. I'm going to let x equal 2. If I do that, I'm going to get negative 2 times 2 squared. It's going to be negative 2 times 4 is negative 8. Plus, I plug in 2, I get 5 times 2 is 10, so I get negative 8 plus 10 plus 1 equals, now I plug a 2 in here, I get 2 minus 1 is 1, 1 squared times a is just a, plus, and I actually know what a is equal to 1, so that's just a 1 right there. In fact, I could have erased the a. Once I learned here that a was equal to 1, we could have just erased the 1 off of there. So we get 1 plus b. b times, we're plugging in x equal to 2, so b times 2. 2 minus 1 is 1, so we'd be multiplying by a 1, so we probably don't need to write that. And then plus, we get 4 times 2 is 8. And now we can simplify things a little bit. So this is going to give us a positive 3 right here, equals 9 plus 8 plus 1 is 9 plus 2 times b. Subtract the 9 from both sides, we get negative 6 equals twice b. Divide both sides by 2, we get negative 3 is equal to b. So once we've found a, b, and c, we know what to put here, here, and here in order to decompose this original ratio into a sum of 3 ratios. So I've set this up on the next slide because I knew this slide would run out of room. So on the next slide, I've actually substituted in the values for a, b, and c. So here I've substituted the values for a, b, and c in. So finding the original integral is the same as finding this integral right here. So now we can continue to work down the page. The antiderivative of 1 over x is easy. That's the natural log of the absolute value of x minus, this will be 3 times, I have a linear binomial down here, so I'm going to get the natural log of x minus 1, absolute value of that. Take the derivative to verify the work if you need to. And with an x minus 2 squared in the denominator, this is the same as having an x minus 1 to the negative 2 in the numerator. So we know when we integrate that we'll need to, I'm going to put a plus to start with, we would need to make, on an x minus 1, we would need to make the exponent 1 bigger. So if we do negative 2 plus 1, we get just negative 1. And then we need to think about what would happen if we took the derivative of this. Well, the negative 1 would come down and give us a negative, but we need a positive right here. So I need a subtraction. So that negative 1 coming down when we take the derivative gives us a negative, and a negative is a positive. The derivative of the inside function is going to be a 1, and I need a 4 up here. So I'm going to need to include a 4 if I want to get a 4. And that should be the antiderivative. We can leave it with the negative exponent or move the x minus 1 down into the denominator position to get a positive exponent. Either way is correct. We need plus a constant of integration. And here we could use some log properties to change how this is written. So for example, the natural log of x minus this 3, which is a coefficient on the natural log, could actually come up into the exponent position on the x minus 1 using log properties. Minus, if you hate negative exponents for some reason, you can get a positive exponent on that, plus c. And here log property says I have the difference between two logs, so that can be rewritten as a ratio, x over x minus 1 quantity cubed, absolute value, minus the 4 over the x minus 1 plus the constant of integration. And that's probably about as much as we could do with this one.